All right, so we have concluded now the first part. And so first, before we continue, I'd like just to thank Tim for the first part, right? And so now in the second part, we will have a bit more exercises and a bit like longer times of exercises. And in the end, I will go through solutions. A part of the solutions today, a part of the solutions tomorrow. We will see as you advance. Yeah, and now at very first I will do a very quick like introduction or some thoughts, you could say, on supercomputing. What is relevant? Let's say if you are a bit new to that, right? So you say you want to start doing supercomputing, solving really large problems. A supercomputer like this one here, for example. And so we think, okay, what to do first? And so many people would say, okay, just parallelize your code, right? But we want to start a bit earlier. You want to first rethink your algorithm. You want to find an algorithm that is really suited for massive parallelization and also for distributed parallelization. And if you just use an algorithm that was the absolute top in the 90s, let's say, to run on a single notebook, it will not necessarily be the best anymore now. Even if on a single notebook now, it would still be the best, right? And so what we want to have are iterative algorithms very often with few global communication. And with global communication, we mean communication that involves all the processes at the same time. And so one solution that we use in our projects is stencil-based applications together with the pseudo-transient method. This is just an example, yeah? And so in this course, we will actually do exercises with stencil applications. And all right, so you say, good, I have revised my algorithm, right? Now, how do I continue now? And so maybe you say, okay, let's parallelize the code. But particularly as we're here doing a Julia course and talking about Julia, we want to not only just get a high-performance code that afterwards is super complex to maintain, etc. We want to make use of this great language, Julia, which allows us to make one out of prototyping code and a production code. We can create abstractions, costless abstractions. We can do metaprogramming, etc. In order to really unite these two worlds of prototyping and production runs at high performance at scale. And so, yeah, this is known as the two language problem, which Julia was designed to solve, right? Prototype can be in MATLAB, Python, etc. Production code in C, C++, Fortran, etc. And so Julia is particularly interesting here because we have in the same time something that can be very simple to use for prototyping, high-level functionality, interactive, and that's not only important for let's say prototyping your domain science application, but also for somebody like me who does building blocks development. It's very, very useful to have something interactive. And so all this results then in very low development costs. And if now basically, why is it in the same time fast and interactive? Well, because Julia compiles the things in a static fashion right before you use it the first time. So when you call a function or a method the first time, it will compile it, and then the next time it will get it from cache, what has been compiled. So the first time, that's why we saw also in sometimes when you do timings, the first time is super slow, well, because it has to compile, right? But as soon as you run it the second time, it's fast because now it can use the compiled code from the cache, from the compiled cache, not to confuse with the cache in the processors. Then afterwards, you think, okay, that's it now, but there is a third step, which I think is very important, which is we want to also evaluate now how good we got, how fast we got, and try to do it in an absolute way, not only say, okay, it's 5 times faster than at the beginning, but we don't know if it's at the beginning was just slow or super slow or terrible, right? So we will discuss in this course also a bit this. And if you have not yet heard of that, there is a term called memory wall, which was said to have appeared, let's say approximately in 2005, where many applications suddenly were not anymore bound by the speed of computation during the floating point computations, but by the speed of accessing the data from the memory. And so for this reason, we will do memory throughput-based performance evaluation. And you will see it is actually, we're actually in good times. You could say it's bad times, but it's actually easier than in the past to evaluate the performance in an absolute way, because what I will show you, you can really do that in a way that one-to-one is one-to-one related to the runtime of your code, and in the end, that is what matters, right? And so this we call it effective memory throughput metric. And so from now on, all the exercises will always refer to this metric. In order to get an understanding of it and to understand how far are we away from where we possibly could get with our performance. All right, so I introduced like 3 issues, and now I will go through the first notebook, which you have already cloned, I suppose, if you follow the instructions on Slack. And so this notebook will be in main memory access. I will really just go through. You don't have to do any exercises there. And afterwards, there will be exercise 1 on data transfer optimizations. I say transfer because I really want to kind of highlight that it's really about how data is transferred from the different places in your computer to another, whether this is from hard disk to memory of the CPU, or from CPU to GPU, or from GPU to the processors on the GPU. This is really the thing that matters. And for most applications, this is really the one and only thing that in the end determines your performance in a practical way. Yeah. And so then we will do more of this kind of exercise then. The second exercise on shared memory as well, as we have done already a bit. And tomorrow we will have some more advanced things. Now all these exercises are again done with CUDA.jl. And yeah, as I mentioned, we will have here exercises on standstill computation. So this is really illustrative, right, to learn something. But you can, if in Julia, if you use exactly standstill computations, you can also use the package that we develop in our projects. It's called Parallel Standstill. So unfortunately, it stopped again for a second. Okay. And so with this, I would like to get started with the notebook. So if you can all now open the first notebook, the memory throughput notebook, and you can execute it, or you can also just look and listen. I will not execute it myself because it takes some time. You can also execute it afterwards. All right, so in this first notebook, we tackle a little bit GPU computing and performance assessment. We have here some very basic, quick overview of what's important for GPU computing, not at all complete, etc. And afterwards we'll get started with memory copy. Now, so as before, and as also in Tim's notebooks, at the beginning we instantiate and activate what we need to have in order to get the right environment. So, yeah, so NVIDIA GPUs are, let's start here, let's say, so we have basically CPU and GPU, right? And what Tim have not yet talked about, I think, is that we have something that we call host, the other thing device, just to make it clear. And so the host is the system CPU, and the system memory is then linked to the CPU, is the host memory, and the GPU is called the device, right? And this memory is referred to as device memory. Just I note these things because afterwards we will talk with this language. Then the GPU hardware is composed of global memory, L2 cache, many streaming multiprocessors, abbreviated as SMs, and each of these contains many compute units, which by NVIDIA are called CUDA cores. This is not at all equivalent to a CPU core, but this is just NVIDIA decided that that sounds good, and so that's how it's called, and you will find it in literature. And the next thing is registers and L1 cache. And this L1 cache can be repurposed into shared memory, depending on the architecture. And yeah, these things are changing from architecture to architecture, that you decide explicitly, or it's automatically decided for you, etc. yeah, we will not go into details here, just so you have heard of it. And now, really, I mean, one of the most fundamental things, as I've already seen with Tim before, is to understand what are the blocks, the threads, and the grid. And as it's so important, I will show it in another way here one more time. And so, in most of the following implementations here, we will want to map exactly one thread to each cell of a 2D Cartesian domain. Or let's say you can say 2D Cartesian, a 2D array simply, yeah. And this figure here, it shows, you cannot see it fully, unfortunately. No, it's fine like that. So this figure shows on the top what will be the domain or the array simply, right? And on the bottom the threads, how they're organized. And they're at the beginning they're completely decoupled, right? But so we decide ourselves that we will map these threads onto this 2D domain in a certain way, and as it's shown here, we'd have, in this case, if we decide to do exactly a one-to-one mapping between threads and array, we will have 4 blocks, for example, with each 4 by 3 threads. Yeah. And the blocks you can see, this is in yellow there. And then now, how does that relate afterwards to the GPU hardware? So all the threads of a block are guaranteed to be executed concurrently on an SM. And so therefore they share the resources like the registers, L1 cache or the shared memory. And so this is really fundamental for the understanding of how you program a kernel then, right? And we also will see that choosing these parameters, blocks and threads, is really, really important for the performance that your GPU application will get. So we will experiment a little bit with this, such that you get a practical intuition about what's the effect of these parameters. But right now, very first, just here, quickly give you a memory copy kernel, which exactly uses this block thread layout. Yeah. So we have 4 by 3 threads and 4 blocks, and that's what we use here. Let me show that. Up. So we have here 4 by 3 threads and 2 by 2 blocks, right? So this will exactly compute what we have seen above. Now, so when we compute, when we play with GPUs, there are certain rules, as we have seen already a bit. You can have maximum 1024 threads per block, current GPUs. Then the maximum number of blocks that is possible is absolutely huge. So you don't have to worry about that normally, because when you map even one-to-one on an array, thread to a cell, right? A one-to-one mapping. Even then, you will normally not run out of the available blocks possible. You will always stay below this maximum number. Thinking that usually you will have threads per block of more than 128. That's just a number that comes from experience. And something we have not seen yet, you can also have a 3D layout of threads and blocks, which is just the analog of what we have seen so far, but just in 3D, right? And so this maps very nicely then to 3D arrays. All right. So now we get started with the more practical part. So we will here, in all these notebooks, do a little like performance laboratory with CUDA and benchmark tools and maybe some other things in other notebooks. And so now we get to this effective memory throughput. And so I said already, okay, we have seen that this memory wall appeared somewhat 2005, year 2005 or more or less, appeared this memory wall. And so we have now an imbalance between how many computations we can do per amount of numbers that we access from main memory. And we can quantify this imbalance. And so that's done here. So it is quantified by dividing the computation peak performance in gigaflops by the memory access peak performance in gigabyte per second, and then multiplied by the size of a number in bytes. And for simplicity, we use here the theoretical peak performance values as vendors specify them. And so, for example, for the GPU that we use here, it is here this 58, right? So this 58 means that we can do 58 floating point computations in double precision per number that we access from main memory. And this is a really big number, yeah? And exactly for this reason, the performance is very often now determined by the speed of accessing the memory and not anymore by the speed of the computation. And so in this course, we will just say, okay, floating point operations are for free. And we only think about the memory bounded, the memory accesses. And so now we start investigating the performance of different ways to express and launch the GPU memory copies. And we will wrap all of these memory copies in functions to enable the GPU, the Julia compiler to optimize them the right way. Because when you do everything in a global environment, right, just like a plain script without functions, then Julia doesn't do cannot do so much in terms of creating generating a good code. Now there exists already a function copy2, which permits to copy data from a pre-allocated array to another. And so we start looking at the performance of this. And I hope you really bear with me with going through this different way of copying memory, because it's really the thing that determines the performance, right? So that's why we really want to do these little exercises here. Okay, so here you saw that we allocate to arrays and benchmark the function using benchmark tools. And then we get some result, right? Some as we did until now in the course. It is some amount of time, but let's say if you're not experienced like Tim, you don't have a good idea of how much time it is supposed to take. And so it will tell you maybe not so much. It will not tell you whether it's fast or not, right? Or how close you are to the possible limit. And so so that is why afterwards we will compute here in now this total memory throughput, which is 2 times the size of the arrays times the amount of bytes they occupy in the memory, and divided by the time we took to copy it. And the factor 2 here is because we have 2 arrays, right? Let's say we have one array from which we read, the other we write to. And so we get this number 2. Now, we still don't know if this is now good or bad. And so that's why we need now to look at what it's supposed to be. And the T-peak is the peak performance. And you can find that in vendor publications. And according to a source publication, you can find that it's 559 gigabyte per second. And so we see that we are like more than 2 orders of magnitudes below that. And so we will now see how we can get closer to this. And if you look at the vendor announcements, if it, here. So the vendor announces for our GPU 732. So also it is what you actually measures. What you actually measure, right, as peak performance is below what the vendor announces usually. So you want to do your measurements, figure it out, or you want to also check in literature what others have found to be the peak performance. Yeah, little detail. So the gigabyte is not the same as the GIB with the I in the middle there. So the GB is 1E9 exactly, 1E9 bytes, like the vendors use it in their publications, and as it also is was shown in this publication that I referred above. All right, so with that we can now continue and really get to the experiments. So Now, why did we get that bad result? Well, the first answer is very simple, because we copied a very small array, and GPUs are just not sufficiently used with a small amount of data. And so we need to work with big arrays to get good performance. And this is really something that I think it's trivial, but you often see in forum, etc., why is my code slow? Well, the first answer is just because your problem size is very small, or let's say it's medium or whatever. It needs to be big in order to get a good performance. So you really want to saturate your GPU in order to get a good performance. So now we see here how it behaves, the memory copy, with increasing number of array size, and you see that the performance increases, and yeah, I mean the exact values don't matter. It's just you see, you make this observation. And so we will use this kind of code here to check the importance of a parameter many times in these notebooks, in order to get a feeling of how these parameters are important. All right, so now we got T-peak. We got the throughput measured as 522 gigabyte in when I did my experience in the beginning. I don't know, sometimes it's a bit lower here when we run it interactively in Jupyter, etc. But let's say this was the numbers that I measured when I run it directly without Jupyter. And so we get this, and it's very close now to 559, like we saw in the publication, but there's still a difference. I mean, we just do a memory copy. Should there be a difference? Maybe not, right? So we want to see if we get closer. And in order to get closer, we will now store the optimal array size that we found with this code, in order to reuse the optimal array size, right? And afterwards, you change other parameters. Now we create our own memory copy function with array programming. A equal B here with broadcasting, and then we benchmark it, and we get here 593. So for something very generic like that, it's very nice, right? But it's still a bit below as well. So we go to GPU kernel programming, and we do just a simple kernel here, really the most basic thing. And now we get, now we say, okay, we start now with just one thread, yeah? In order to see what happens if we run only one thread. And you see the performance is very bad. We get only to 9 gigabytes per second. And okay, to be clear, we run one thread, but we run the amount of block necessary to still span the whole domain, the whole array, right? So we will still, and we have still the same concurrency as when we would run with more threads. We have still the same, let's say we have the same amount of threads, but organized in a way that we have only one thread per block, right? So I hope that made it clear. And with that way, using only one thread per block, we get to only these 9 GB per second. So that's clearly not the way. And so as we have seen already before a bit, so we have to use 32 threads at least to get something that makes sense, because a warp has the size of 32 threads. And and as soon as we do that, we already get now that this is 300 GB per second. Still it's much better, but still not good, right? And now, so we want to see how does it change if we increase the number of threads from 32 to the maximum possible, 1024. And we see now that already with 64 we get to nearly the result we should get. Now, these values, they will change from architecture to architecture, what exactly you will see. So it doesn't matter what exact values we have, but it's about the understanding of, like, to get an intuition what it means to have only one thread or 32 or more per block, right? And but now, very important, we can also increase the number of threads in the second dimension, but we still keep 32 in the first, because we want to always have the threads within one warp access a contiguous chunk of memory. And we see that we get, also in that way, we get similar results as just before by increasing only in the first dimension the number of threads. And I think it doesn't matter, but that does matter, because we can now this way launch the threads in a 2D fashion. And when we, for example, do stencil computations, we want to compute the derivative not only in the x direction, like the first dimension, but also in the y dimension, the second dimension. So we will have much better cache use, much less cache misses, and so on. You know? Now, unfortunately, we have this limit of 1024 threads, right? So we cannot just do the same in the same way also for the third dimension. If we have a 3D problem, that would be lovely, but we don't have the possibility to have so many threads per block. All right, so now we have seen just a simple memory copy, and but we got still not to the result of the publication. And so we note one thing if you read the publication, that they don't actually copy one array to the other, but they do they copy two arrays rather to one, because typically in application we read more than we write. Yeah, so I guess also for that reason the hardware performs better when you read more than you write. And so now we have here this C in addition, right? We read also the array C. we do the same again, and ta-da, we now got 561, which is even 2 gigabytes per second better than the best result shown in this publication, where they used C++, Cocos, a lot of different things to try to get the best memory copy result. So it means we're really there, right? It's really excellent. Julia is really on par with the others. CUDA.jl is on par with the others. Yeah. So nobody can say, if you would use C++, it will maybe be faster. No. Now, there is just one little detail. So usually, one in the publications uses a triad kernel, it's called. And so when we have also a scalar S, and when we do that, when we add that, we get the same result, because just adding a scalar doesn't change anything. Okay, so we have now, with this, really established that we can do practically do a memory copy the way that people in publications show is the maximum we can do, right? So we have achieved our baseline. And so in the future exercises, we will always try to stay as close as possible to this memory copy when we do our whatever computations we do. We will always refer to this memory copy to link back to this memory copy speed. Now, yeah, also if you do just GPU array programming, this triad, we also get a good result, just to show. For simple things like that, GPU array programming is really convenient and works really good if you're not really in a hotspot where things have to be really optimized to the maximum. Okay, so before we continue now with the exercise, we just want to remember the parameters that we found that are the best, and because we want to reuse now these parameters we established here in the exercises that you will solve now. Yeah? So we found here that the best array size was 16,000 something, the threads was 32 by 16, and all the blocks are these, which are automatically derived from the thread size and the array size. Right. So with this, I would like you to get started with the first exercise, so the second notebook. All right. So I will walk now through the solution of the notebook with the first exercises. So that's this one. So the idea was to learn how to minimize redundant main memory transfers and understand its importance, and understand the limits of the total memory throughput metric for performance evaluation. Total memory throughput is also something that you would get from a profiler, right? So it's this really the throughput where you count every byte, as opposed to the effective memory throughput, which is the next objective here, where we only consider what we think is important. We come to the details later. Okay, so we consider this diffusion solver, 2D diffusion solver, very simple. And we had here this diffusion step, so step one iteration, one update, one time step. We had this computed here with array programming. Just a straightforward implementation, very directly from the equations, which you see on the right here. On the right here, yeah. And so we got this kind of diffusion, like you see that here. And then we benchmarked it and computed the total memory throughput, actually a lower bound of it. Now, how did we do that? Why do we say here that it was 11 times that stuff? This is because we have, when we look at the code, we have, when we count here, actually 11 times that an array is either read or written without considering that we access neighbors. Because we say when we have neighbors, at least some part of it is going to read from cache. And so it's a lower bound because, yeah, maybe something is not read from cache, but that's good enough here to consider a lower bound. So we know at least 11 full array accesses are done. And also we know, right, that we have this full access because each statement will create a separate kernel, each broadcast statement. So we have here 4 separate kernels in these 4 lines. All right, so so we computed the total memory throughput lower bound and got 384, which, if we compare it to what we got before, this 560 as peak throughput, doesn't seem so bad, right? But actually, we are very far from where we could get with such a solver. And in a moment, you will see why, in case you did not yet. Now, in order to do it better, we want to have only one statement, one broadcast statement, instead of 4 like before. And to do that very easily, we will just mathematically change the equations that we solve. So we will solve this here now, where we basically substituted the fluxes just into this expression here, and end up just with a single line here, without fluxes, without dt. And then so we program that here. So it's a single statement. It's in multiple lines, but it's a single statement, right? Here is in mathematical way written what it is in the left. And so just by doing that, just by doing this change compared to what we had before, we already get then a 2 times speed up. And but if you look at the t-tot lower bound, it actually decreased. So we got the 2 times speed up, but the 2 times decrease of the total throughput. So this already makes it clear that really the total throughput cannot be good, because we computed it cannot be a good metric, right? Because we computed the same thing 2 times faster, but yet here it says it's the performance is 2 times lower, right? And yeah, so we store here just these values to later be able to compare against it. We go to the next task here. And so now we say, okay, we want to rewrite this function now using GPU kernel programming. And we realize actually that yeah, so this is then a simple implementation with GPU kernel programming, very direct. And so we benchmark it as well. And now we get a 5 times speed up compared to before. And t-tot is similar as before. And so, yeah, now we have very clearly seen that t-tot, so total throughput, is a bad metric. So we define here the effective memory throughput metric, TF, and we define it that way, where so the effective memory access, AF, is the sum of twice the memory footprint of the unknown fields, DU. And so these are fields that depend on their own history, that need to be updated for every iteration, and that's why they need to be stored in main memory, right? Because we need the history. And the known fields decay, they do not change, but they still have to be read. And so we have to consider them also. The factor 2 instead of DU is because we have to read and write, right? An update is read and write. Decay so without this factor 2 because we only read it. And then after that, very simple, the TF is equal AF over TIT. And so for this, the upper bound of the effective memory throughput is T peak. Just like we measured it in the very first notebook, you know, where we got 561. So T peak is 561. And just as a detail here, so we assume here that we evaluate an iterative stencil-based solver, but we will see tomorrow that we actually can use the same kind of metrics also, for example, to see how good is our cumulative sum implementation that we'll look at. So it is something that we did for this kind of solvers, but you can apply it or slightly modify it to other, to evaluate other kind of computations. Then second, we assume that the problem size is much larger than the cache sizes, and the usage of time blocking is not feasible or advantageous, which is something reasonable to assume for real-world applications. I'm not going to talk about what time blocking is if you don't know. So what's very important here is that we do not include fields in this effective memory access that don't depend on their own history. So exactly the fluxes which we removed before, right? We could see we could remove them and still compute the same stuff. So these kind of fluxes, we don't consider them in this metric exactly because we don't necessarily need them. So because they can be recomputed on the fly or stored on chip or whatever. So then we compute the now with the new metric, we compute it for each of the results we got before. We compute the effective throughput metric, and we get 100, 200, and 500, right? And the speed up, and then afterwards we can say, okay, what happens if I try to compute the speed up now based on this metric? And do I get the same as I had before as speed ups, right? When I consider the time, and it happens to be true. So this shows that this metric really will show you when it's high, the value is higher, that the time to solution is accordingly lower, because it's proportional to time. Fully proportional, yeah. Then we can, in the end, say, okay, now we did other. How good are we now? How close are we to the theoretical upper bound? How much room do we have potentially to improve still? And when we see here that we are at 92% of the T peak. So we can at most improve this solver by 8%. And there's no way that anyone could do better, except if you use time blocking, like I said before. But it's not if somebody would say, okay, but if you would do it in C++, I could do it faster. No, you can't. The theoretical upper bound is 561 gigabytes per second, no matter what language you use or whatever you do, right? Yeah, so this concludes this first part. And just to show, now you don't, for example, if you are actually interested in stencil computations, in our projects, we work with that a lot, and so we have created HPC building blocks. And so the second order formulation, with second order derivatives, you could compute it like that, in a single line here, right? And if you would like to do it with 4 lines like before, with the fluxes explicitly noted, then you could write it like that. But in the end, it would do the same, because it would automatically generate a code that would compute Qx, Qy, and Qt and DDT on the fly. You see that here, these arrays do not occur here in the signature of the function, because they will never be read and written from main memory. And then the kernel call would be simply like this, with a parallel in front of it, and it will automatically choose some good launch configuration. Okay, I will now give you a little, very short glance into the project that we have been doing, just to show what kind of HPC building blocks one can do in Julia, and in order to have a sustainable development, where it's afterwards very easy for domain scientists to program, right? I will go very quickly through this presentation, which was at JuliaCon half an hour. I will leave away certain things. So the talk is about scalable 3D PD solvers tackling the hardware limit. And I presented at the very beginning that we want to solve with Julia the 2-language problem. And one can go kind of one step further look at it a little bit more generic or general, and say we want to basically solve this challenge, the performance, portability, and productivity challenge. And everybody in HPC talks about solving this challenge, right? And so here is our solution, where with the colors on the left, I will show which part of our solution corresponds to each of these aspects. So first we have algorithms, and so as I told you already before, we use iterative accelerated solid transit method because this is scalable data local algorithm. And then the programming language, obviously Julia, for its reasons we already talked about. And for now, to get within Julia performance and scalability, we use automatic shared and distributed memory parallelization and optimization of architecture agnostic code. And so look at the, so productivity is in violet, right? So automatic is for productivity. The next stuff in red is for performance, etc. Yeah. And so that's why we create building blocks that would allow us to do that. And concretely, these two packages, parallel stencil and implicit global grid, where the first one is for stencil calculations on a single node, and the implicit global grid is for the distributed parallelization. And performance evaluation, we do exactly use the effective memory throughput as we talk about it here in this course. So this is the summary. So very shortly on our building blocks, we have many requirements. We want to use automatic differentiation, level set approach, etc., etc. Occasionally want to do explicit low-level programming, have compatibility with other Julia packages. So our building blocks should respond to all of this. So we want to have something domain-specific, yet also generic and seamlessly integrated into the Julia world. And yeah, so these are the building blocks mentioned already. And particularly interesting maybe also is that in parallel stencil we have automatic differentiation support powered by enzyme. And everything works also an AMD GPU and CPU, of course. And so we have already seen these examples. Oh, sorry, this would be interesting. So we have, for example, a macro here called height communication, which allows in the block that follows here, we have the computation. Afterwards, we have boundary conditions and upload halo, and it will automatically put the first on one stream and the halo update on another stream, and so allow to overlap this. And you don't even have to do anything; you just specify like that. We would all do behind the scenes. And yeah, and that's as a result, everything is runnable on a single core or on thousands of GPUs. So this is exactly what I meant earlier, that we want to have things that are that the production and prototyping becomes one and the same, that we don't need to have two different worlds, right? We can do some generic programming, use some low-level constructs, and here in particular, just with this we can say, instead of running the kernel, instead of computing the kernel, we can say we want to have an automatic differentiation with respect to these variables. That's all you need to do, and you will get automatic differentiation. And then we have some automatic optimizations, where we just have to set a flag and we do everything. And so it will use shared memory, etc., steer register usage to avoid redundant memory accesses, mostly, right? As we see in all these exercises. And at the same time, it will automatically determine the launch parameters, how much required, how much share memory is required, etc., etc. It does all automatic. So here, that we have seen already in the course. So then we'll finish with some benchmarks here. So we had some benchmark where we have with parallel stencils with mass close notation of a heat diffusion kernel, like we have it in the course. Just here it's in 3D instead of 2D. Then here the same with array broadcasting. Then a kernel programming solution with parallel stencil. Then the same here with CUDA. You see the only thing that changes from CUDA to parallel stencil is this indices computation, which has to be done explicitly here. Then we have the same in kernel abstractions. Afterwards we have, now with parallel stencil and mass close way, the way we want to potentially write the real-world application with many equations, right? And the same thing with array broadcasting, so we call with 5 equations here. I called it a 5-equation-based benchmark because afterwards in the solution, in the results, you will be able to recognize what I meant, right? And so here we got the results. So you recognize this number immediately. In the first notebook, we actually could see where it comes from, and we could see that it is even 2 gigabytes per second better than the best reported in the publications, where they used C++, Cocos, etc., to try to get the best. And then you can see here from left to right increasing performance, right? And so the worst is obviously the broadcasting with 5 equations, because we have 5 array statements, and so it will create 5 kernels, so it cannot reuse a lot of data, and it has all these fluxes stored in main memory, right? It has to read and write them. Then afterward we have the broadcasting with a single statement, like you also did in the exercise in 2D. Then afterwards you have the explicit kernel abstraction solution with the kernel, right? And with kernel abstractions you can only write kernels. And then the corresponding CUDA solution, which is actually better. That was a bit unexpected that we would have such a big difference. So there is some overhead in kernel obstruction at some place. And you could see that the only difference was really there was absolutely no difference in the code itself. The only difference was the way it computes the indexes, right? It was the only lines that were different. And then afterwards you have all the solutions with parallel stencil, and you can see they're all very good and similar and significantly better than the others, thanks to the automatic optimization that are done. And so particularly interesting is here this mass close with 5 equations. So even writing it really in a way that you would like to have it in a real-world application, we can get the same performance as with the more explicit way of writing things. Yeah, on the right you see CPU results, which are not really of interest for us. Sure. Could you maybe take the mic?
No, I can.
Okay.
This other one, is this also the runtime? Can we say it's the same? That the code is standard with this matrix, it's the same with the runtime, or?
Here. Yeah. Yes, exactly. As we saw in the exercises, this metric TF, right, is proportional to the runtime. So if you make the same plot with the runtime, you will have the exact same results, well, just inversed, right, in terms of the plot. But you will have the exact same results. So let's say if you would do it with speed up computed by runtime, you would have exactly the same plot. And not just approximately, really exactly, right? Because it's just the runtime multiplied by some values, right? Yeah?
Why is the math code slower than math code by equation? I mean, is that a significant thing, or is that just...
Okay, so the question was why this mass close here is slower than this mass close with 5 equations. I mean, the difference is very small, and I cannot at this point tell you why now. Yeah. And here there was like a comment why is CUDA so small, so slow compared to these. Well, because the CUDA kernel is a straightforward kernel without specific optimizations, using shared memory, controlling registers, etc. It's not that CUDA is doing bad. It's just a straightforward implementation, and here we used automatic optimization.
And this automatic optimization also changes the kernel content, or only how you call the kernel? So the number of blocks and threads and something like that. Or it's also the kernel content different?
The question is whether
such a simple kernel in some sense.
The question is whether the optimizations change only the kernel content, or like how it's written, or also the launch parameters. So the launch parameters are the same for the kernel obstructions and CUDA, and they're in general based on the same like heuristics, but here we have actually a grid-striped loop, which we'll see more tomorrow, in order to be able to make better reuse of registers, of values with registers. So yeah, there is a slight difference in that, but the difference is not because of this kernel launch configuration, because if you would remove the optimizations, then you would get something similar to this. Yeah, if you would just do a grid stride loop and no other optimizations, you would end up here. All right, so I'll continue. Yeah, and so with that, besides that we get good performance, we can scale it to a large number of GPUs. Here we run it up to 2000, and we get a parallel efficiency of close to 94% here. And then we have also good initial results on Lumi with AMD GPU, close to 97% parallel efficiency. And we get here these good results also thanks to hiding the communication behind the computations, like I outlined earlier in the presentation with this hide communication macro. Yeah, so that's all. That's all I wanted to show, just to give you an idea about what we're doing, and to show you that with Julia you can really create HPC building blocks that are that give you performance like you could have it in C++. You don't have any problems here to get to the same kind of performances, but you get an incredible nice environment for the main scientists to develop stuff, and also for people like me to do HPC building blocks in an interactive way to very easily do things. That's all. All right. Good morning, everyone, and welcome to the third day. I will do a very brief introduction. Also, because yesterday I already showed you the talk from JuliaCon, and so I told you quite a bit of things of how we would like to do large-scale supercomputing. So it will be very brief. And so yesterday I said, okay, the first step is not immediately to parallelize the code, but we want to revisit the algorithms, and so I said a good solution is iterative algorithms with few global communication, like stencil computations with the pseudo-transient method, for example. And so if you're not familiar with that, what that means to have a distributed algorithm, this is how you could do that if you want to run the multiple GPUs. If you have, for example, stencil computations, right, where you have very local computations. So you have a global grid here, which is like where you want to solve your problem, your domain. And then you split that into 4 grids. That's typically done like that. And now in the stencil computation, you would exchange at the boundaries values with the neighboring processes, such that it appears as if it was actually one single connected domain. And in order to have this be possible, even if you do something else than stencil computation, it's very important that you have data locality, that you do your computations with values that are close together. in the memory. If your algorithm in general is accessing data from everywhere in memory, if you run it on a single computer, for example, then that means also at scale it will not be good, because you will have to send data from all the processes to different processes. You'll have a lot of communication between many processes, and possibly a lot of global communication also, where all processes will have to communicate together, and this is very costly at scale, yeah. So the ideal case is just if every process only needs to communicate with his direct neighbors in whatever topology you choose to have. Now, here we concretely would like to have an implicit domain composition. So we do it not like most people do it to say, okay, we have the global grid, and now we split it. No, we do it just the other way around. We say we start from a local problem, and then we just repeat that local problem as many times in, for example, x direction, y direction, and z direction, until we get the global grid of the size that we want. And so concretely, we code basically what happens on one GPU, and then afterwards, we just add this communication in order to have afterwards the global grid problem. So in this case, I think it has been clear by now. We would use 2x2 GPUs and arrange them in a 2x2 fashion in x and y dimension in order to get to this global grid. And so the big advantage of this, compared to starting from the global grid and splitting it, is that we can easily choose the size of the local problem such that it has optimal single GPU performance. Because as you have seen when we played with the parameters, and one of them was the size of the grid, right? At some point it was an optimal performance with a certain size. And so for our problem, we can determine the optimal performance and then afterwards scale it up that way. If you do the other way, if you start with a global grid and then you split it, then you will just get whatever happens to whatever you need to have on the local grid in order to get to this global grid, right? So, yeah. And in addition, the domain decomposition is completely trivial like that. I showed you yesterday some scaling, and here I have some more. Yesterday I showed you some on Lumi ice sheet flow solver, and here we have another one as parallel scaling on pitch stained here some years ago already. This was a 3D pore viscoelastic two-phase flow, and actually here we have made a comparison between CUDA and Julia, a solver, right? But I mean, it doesn't matter so much here, because here it's only about the scaling, and we got very good scaling in both cases. Actually, with the Julia code better, but because we have improved the MPI stuff meanwhile. And yeah, the message is just we get a really good scaling, which flattens out for many GPUs. And so, I mean, if you would go further, it will just be a flat graph. We will scale to how many GPUs we want, to the biggest supercomputers. Yeah, so with this quick introduction, now for the agenda today, I would first like you to continue with where you were yesterday, so to finish the second exercise notebook, that means the third notebook of all, and then start with the fourth notebook, and then, depending on how you progress, I will go to the solution earlier or later, probably rather soon with the second notebook, the second exercise notebook, and yeah, and then we see, right? Now, so the notebook you started yesterday already was with shared memory, now applied to the diffusion code. And so we have seen with Tim already a bit shared memory. So if that is already enough for you, you can just maybe look through the solutions and go to the fourth notebook, where you will have the most advanced content, which is where we try to like steer the register usage. And in the very end, you will have also exercises with warp level functions. So yeah, there you can really get to the most advanced things. And then the last exercise is about a short introduction to distributed parallelization with MPI. But this is really an introductory notebook. So if you're already familiar with that, you better spend your time on the fourth notebook. And also the last notebook will not be done in such a rigid way with always comparing against peak performance and so. It will be just a bit showing how it generally works. Yeah. So the fourth notebook might be the most interesting for most of you. All right, so happy work with the notebook. All right, so I will go through the solutions of exercise 2. So this is the third notebook of all. And so the goal of this exercise was to learn how to use shared memory to avoid main memory accesses. So we considered here the same diffusion code as before, 2D diffusion, and started by doing a little benchmark exercise where we fixed the number of threads in X dimension to 32 and increased the number of threads in the other dimension. And so you see here that the compared to the just memory copy, it is more sensitive to these to the launch configuration. And you see, not anymore with just higher number of threads, you get in general better results. But you have here a sweet spot at 32.8, and the reason is that as the on the shared memory on the streaming processors, all these resources, cache, shared memory, registers, they are shared, right? So if we don't have the maximum amount of threads, each thread has more of these resources available. And here in particular, each thread has more, there's more cache per thread available. And so the sweet spot seems to be at 32,8. And in many applications, I've actually experienced that it's really a good value. Of course, in this kind of sweet spot, there will change potentially from architecture to architecture. So it's also good to try to sometimes again do this little benchmark exercise to see for your particular problem, for your architecture, what is the best. So then afterwards we say, okay, we want now to use shared memory, which is repurposed cache, high-level cache, and as a starting point, we want to link it back to the memcopy triad, which you see here. So we start again just with a memory copy with this, where DT is the scholar, right? So it's exactly the triad from the first notebook. And obviously when we benchmark this, we will get exactly the same result as before. The peak performance that we measured, 561. And so this is a perfect starting point. And now what we first want to do here is to just read the data not directly from memory and do the computations, or well, this simple plus computation, right? Not just do this, but in addition, read that through the shared memory. So we allocate an array, shared memory array of the right size, and then here we use that. So T_L is here the shared memory that we allocated. Right? So just read the data through the shared memory. And doing that, as shared memory is super fast, we don't lose any performance. So we can go to the next step, where we say, okay, now we will need to have also, we will need to read also the neighbors at the boundaries of our block, of our thread block, the neighboring values. And so we need to have a shared memory array that is now two bigger. So we have like a little halo around our block. And so we do that. And we need to, of course, also adapt here the shared memory specification, where we say how much shared memory we need. So we have here a +2 now compared to before. And but you see that the result doesn't change yet. We have just allocated more, but it's not so much more. So we can launch the same amount of threads and blocks, etc. So no change in result, performance result. And so now the next step is then to actually read also the values into this halo, right? The neighbors of the threads that are at the boundaries of the block. And so this means now we read more data in per thread block than before. And as a result, we get a worse performance than before. We haven't done any more computations. We have just read in additional data. Yeah. And actually, when I did the test without Jupyter, I got 538, just to remember this number, because I will refer to it in a second. Because now, in the next step, we now finally add the actual derivatives to the code. So all this stuff here, right? We add the derivatives, and so maybe now you think, okay, but now we have a lot of computations. Will it now affect the performance? And with the result that I did when I did nothing interactively, I got exactly the same result, yeah? And that's what it should be, because we don't do any additional data movement. Yeah, and so we have successfully created a solver using shared memory. I mean, very simple, and it's in 2D, so the effect is not very big. In 3D, the effect is much bigger, depending on the architecture as well. But it's much more important to do optimizations. And so finally, we can check how close are we to the theoretical upper bound. And we see that we are now here nearly at 95% of the theoretical upper bound that we can achieve with this solver. Then just to conclude, so if you're interested in stencil computations or something similar, you can use parallel stencil, as I mentioned already earlier. And so you can also explicitly allocate shared memory. You see that a shared mem macro, and do all these kind of things in a completely architecture agnostic way. So this code will also run on the CPU and on AMD GPU, for example. All right, so with this, we conclude the morning, and we can go for lunch, the same place as yesterday. All right, so I hope you enjoyed all the supercomputer visit with the machine room cooling system. And so we go back from the physical world to our abstract world here on the screen. I will go through the last solutions a bit quickly, maybe because everybody's tired. And in any case, you have all the solutions available on GitHub, right? So the objective in the last notebook was to learn how to control, or let's say steer, registers for storing intermediate results on chip. Learn how to use shared memory to communicate between threads within a block. We have done that already before, just a bit more. Learn how to use warp level functions to communicate between threads within a warp. So for this here, we used the CumSum function as an example. And if you look at the help, CumSum is the cumulative sum of A along the dimensions dims here in this function, storing the result in B, right? And so here we in this example, we only looked at 3D arrays, and then we created just one function for each dimension separately to have it as simple as possible. And so we got here started saying, well, before we actually start to implement something, we want to think about what is how can we afterwards check the performance? So we want to come up with a metric that will be useful to see how much room for improvement we have. And so we create a metric, effective throughput metric, similar to what we used before to evaluate the performance of the diffusion solver. And it's very simple. In the CumSum, well, we read one array A and we write to one array B. And so we just have two array reads, right? Array accesses, full array accesses. And ideally, it should not have to do any more than these accesses. That's the ideal case. So that's the theoretical upper bound for the CumSum. And so we called it TF_CS to refer to it later. Now, we saw that in the first notebook, in the memory copy notebook, we saw that when we copied exactly one array to the other, and not two array to one, right? Not the triad. When we did that, we got actually 550 gigabyte per second. And so we will use this here as the T peak for this example. And so we start here by modifying the memory copy code from that was doing a 2D indexing, and we add here IC, a third index, and have here now 3 indexes, right? Also IC. And we use like before. We found 32 and 8 is good, and the last one you use only one thread. And like that, we evaluate what performance we get, and we got 538 here. So we still, let's say, we got a good performance in memory copy with that, and we say that's enough now for this exercise. And so this is our starting point. And so now the easiest way to do a CumSum is if we can do it completely serially in the dimension in which we want to take do the CumSum. And so we start here doing it in the third dimension. And so we make a loop over the third dimension. Because afterwards we can then just add up, right? But at this point we just check now what is the memory copy throughput that what is the throughput that we get with a simple memory copy accessing the data that way. And so we see that the performance is still very good, a little bit less, but still very good. And here, of course, we verified that the results are also true, comparing against the original value. And so now that we have found that this is a good way to access the memory, we can now simply add here a value, a local value, which then will become, in normal case, a register. And we can accumulate here then the CumSum in this register and write it back to B then, the result. And doing that, you see, we get the same performance as we got before, but without doing the actual CumSum. So we didn't lose anything at all in performance by actually doing the CumSum, as it's all done in registers. And here we have just a comparison to the CUDA.jl generic function, and well, in this case it is much better. So it verifies that we really did already a good job with that. Yeah, I mean, in the generic functions you have much more things to take care of, much more cases to consider, right? Now, so after that, we say we can go further to the second dimension to do the same. So we again start with the memory copy. So we don't do yet the CumSum, right? We just do it now over the Y dimension, the loop. And as threads, we take this. And we see that also that when doing a serial access over the second dimension, we still get a very good performance. So this means we just do the exactly same as before. We do the loop, keep the loop, add now the CumSum, accumulate the things in registers, and again we don't lose any performance doing that. And so we get to the third case, the first dimension. And so here now we have just one thread and one block in the first dimension, and do the loop here in the first dimension. And here the situation is very different. Doing that now, the performance is very bad. Right? We still didn't do any CumSum, right? It's just the change of access here. We do it the same way. And so it doesn't make sense to add now the CumSum. It cannot get better, it can only get worse, or it will likely stay just the same, right? Or it should stay the same, but it can get better. And so we first want to change the way we access the data. And so we say, okay, we will take 32 threads in the first dimension, and see what performance we get, and we get now something very, very different, right? Because now we again access the memory in contiguous chunks of 32 numbers, not like before where we took just one at a time. That's why it was so slow. And so now we can take this as a starting point to implement the CumSum in this first dimension. And so we use shared memory, as we have already seen before how that works, more or less. And we do here kind of the simplest possible shared memory implementation. We allocate the shared memory, then we read with each thread the stuff into shared memory, and afterwards, just with the first thread, tx = 1 here, we just then do the CumSum, and afterwards we write it back to the main memory with each thread. And so with this implementation, we get already an order of magnitude better performance than before we had in this memory copy code, right? So it's not perfect, but it's much, much better. And so as we here have only 32 threads, it's an ideal case to use warp level functions, because a warp is of size 32, right? And so we will just do the simplest possible implementation using warp level functions. And so we now read in the data into a local value, into a register, instead of shared memory like before, now in a register. And then we will here with this function shuffle sync, we will broadcast with each thread his value to all the others, you know? And then do the cum sum. And so we have a redundant cum sum computation, and we have, as we have 32 threads, we have 32 calls of this function, right? So it's kind of the brute force approach, the simplest possible to do that. And so what do we get as a performance? We get then this. So not so good. It's much worse than the shared memory implementation. And so we need to do something smarter than before and not just send every value from a thread to every other one. And so we can do that with now a partly parallel algorithm. So this can work like this. We compute the local cum sum of subchunks of increasing size from 1 up to 32 with power 2. And the local cum sum of the subchunks is very simple when it's size 1. It's just a value, right? And then afterwards, when you have a bigger size, then it is the previous value plus the one of the lower half of what we have already computed before. And yeah, then to compute then the global cum sum of the thread, we add the global result to the previous chunk. And then at the very end, we need to broadcast the global cum sum of the last thread, the thread with the highest ID, to all the other threads, because they will need it to compute afterwards again the next cum sum. And so we can use again the same function, but in difference to before, we will now not use it together with all threads at a time, but we will use it using this width parameter. We will use it in small groups. So we will have first we will start here. Sorry, we will start here with e equal 1. So with width of size 2, and afterwards width will become size 4. Will become 4, and then 8, and then 16, and then 32. Yeah, and so that way we will be able to use to send the value of the local cum sum that we want to the other threads that need it in order to complete their local cum sum. And so once we have finished that, we will write then this x-dimension chunk of results back to the main memory. And as I said above, the step 3 was then share the cum sum of the last thread with all the others, such that afterwards, when we here go to the next the next X-dimension chunk, everybody has the global CUMSUM from before. And so doing that, of course, first we see, yes, first of all, it worked, right? and second, the performance is now similar to the solutions that we had before, even a little bit better. And again, compared to the generic solution, we got a 5 times speed up. Note that in future architectures, the generic solutions work much better. Tim tried it out with a more recent GPU, and then the difference was only factor 2. And maybe with an even more recent GPU, it can be even smaller. Yeah, so here in the end, then basically just want to.
Why is it still so bad? I mean, even a factor of 2 is still very significant. Why is still so much better than the standard built-in function?
I honestly don't know. I don't know how it is exactly implemented. It could probably be improved, but I mean, there is a limited amount of time of all people who deal with these things. So yeah, I cannot give you an answer. And so in the end, what remains to do here is to say, now we want to compare our result, our effective throughput, to the peak memory throughput. And as we said before, the peak was 550. And so when we do that, we see that we are now at 95% of the theoretical upper bound. So we could only increase this function by 5% more. So with this, I complete this notebook. And I will go through the other one, but only very fast, because this is more an introductory notebook. So it's an introduction to distributed parallelization. And so the idea is to understand the basics of distributed parallelization and learn a bit about CUDA.jl. And so this material was mostly created by Ludovic Grass. And so at the very beginning, the idea was just to do a fake parallelization. So not to actually use MPI, but just do what you would need to do with MPI, but on a single compute node, and on a single process even. And so we start here with 2 fake processes, and we have here the HL is for, the L is always for left, the R is for right. Left and right, it means the domain, right? The domain is just split in 2. And so it's a very simple exercise to just get the basics of how one can do Halo updates in a simple diffusion code. And so I will not go into details here. So afterwards it shows how to do that with N fake processes, and then it introduces how to do Halo updates with the simplest possible way, using MPI send and receive, which are blocking. And it shows you how to initialize MPI and create Cartesian topology, etc., etc. And then the idea is afterwards to run this diffusion code first each time without activating the Halo updates in order to see what is missing, right? And you will see that you will have two completely disconnected problems that you will be solving, and only once you activate the update Halo, it will be one global problem that you're solving, one connected problem. So the first in 1D, then in 2D, and in 2D it's very similar to 1D, of course. And then afterwards, here a little introduction to multi-GPU. So exactly the same code as before, just adding then the CU arrays, using CU arrays instead of arrays. You will get the first very simple implementation of using GPU, and well, it will be multi-GPU, as you have here these Halo updates already implemented then, right? Yeah, so I mean, these are very simple exercises. If you're interested, just go through them, and if you have not yet been able to, and see what happens with and without Halo update, in order to really understand what it does. Yeah, and then now this is really the simplest possible way of MPI, and to get better performance, you can do a lot of things. First of all, we can use CUDA-ware MPI, where you can pass directly CUDA pointers to MPI. You can, and so this means it will be able to use remote direct memory access. And this is something very beneficial in many applications. But note that it's also possible to get a very good scaling without this CUDA-ware MPI. So actually in this package implicit global grid, we implemented all that, and so also using pinned memory like Tim introduced, and pipelining and everything, doing everything asynchronous as much as possible, you can get to very similar scaling results. We got very similar scaling results. And also something else that of course you can do is to overlap communication with computation, like I showed that with parallel stencil we can do it just with this macro, for example. Yeah, so there is a lot of things that you need to do in order to get really good scaling on large-scale supercomputers. And of course, one of the first things that you will want to change also is not to use the blocking send and receive, but non-blocking. So you can overlap your different communication. Yeah. Yeah, I think with that I said everything I wanted to tell you, and we can conclude the course. So please thank again Tim to be here, and have a good trip home.
Thank you. Also,
Thank you.